Hello everyone, my name is Jillian Kiefer and I'll be your instructor for Math 95 this semester. So as you may already know if you've looked over the syllabus, we will be having recorded lectures while our in-class time will be reserved as more of a discussion time to do practice problems and also to have my office hours as well. So in this very first recorded lecture, we are actually just going to be going over the material that we'll need to know for class tomorrow. As far as going over the highlights of the syllabus, and as well as doing those items that you always do in the beginning of every semester of class. We will do this tomorrow when everyone is present. So if there are any questions or anything like that, we can answer them at that time. So for now, we will begin by jumping straight into our very first chapter, which is the review chapter on fractions. All right, so our first chapter, which is our review section on fractions, we'll begin by going over our objectives of this lecture. So our objectives, we have 8 of them here. So number 1 is going to be we want to identify prime numbers. Number 2, we want to write numbers in prime factored form. Number 3, we want to write fractions in lowest terms. Number 4, we want to convert between improper fraction and mixed numbers. Number 5, we're going to multiply and divide fractions. Number 6, we're going to add and subtract fractions. And as far as this lecture goes, we'll actually only be going over 1 through 6, since we see our objective 7 is going to be solve applied problems that involve fractions, and objective 8 is interpret data in a circle graph. Those are going to be things that we'll go over in tomorrow's class, since those are more of problems as opposed to material we will go over. So we're going over objectives 1 through 6 today. So everyday numbers we encounter can be kind of broken down into 3 separate categories. We often see natural numbers, which are the numbers 1, 2, 3, 4, and so on. We often see these 3 dots, and this kind of represents that it will go on infinitely. So we're imagining 1 to infinity. Then we have our whole numbers, which are actually just our natural numbers with the number 0 included. So it will go from 1, 2, 3, 4, 5, on to infinity. And our last category here is fractions. So obviously there's going to be an infinite number of fractions, since you can divide any number by any other number. So we just have a few listed here. So common fractions, we see 1/2, maybe 2/3, 3/4, something like 11/12, etc. So these are all different types of fractions that we can see. So we can talk about parts of the fraction. So when we see a fraction, we see a number, and then there's a line, and then there's a number, another number below it. So we want to kind of talk about the parts of the fraction. So our number that is on top is going to be our numerator. So in this case, this is going to be identified by A, which we see in blue. Then we have this line, and that's called the fraction bar. The fraction bar represents division. So in the fraction bar, if we say A fraction bar B, or A over B maybe, this also means the same as A divided by B. So our fraction bar is representing this division in our fraction. Then lastly, we have B, which is our number on the bottom or below the fraction bar, and this is known as our denominator. When we do identify this as division, we always say the top number divided by the lower number. So we have A divided by B in this case here. So a note, this is taken from your book. So if you would like to see it in your book, you can always check there as well. But just to note, fractions are a way to represent parts of a whole. In a fraction, the numerator gives the number of parts being represented. The denominator gives the total number of equal parts in the whole. So in our figure here, we have the shaded region represents 3/8, or 3 of 8, or 3 divided by 8 of the circle. So we see our circle, and our circle has been divided up into 8 separate parts, and our shaded part covers 3 of these parts. So if 8 is our whole and 3 is shaded in, this means that there are 3 out of 8 that are shaded, which represents that fraction of the shaded region of ours. of our circle. So fractions are classified by proper fractions or improper fractions. Proper fractions are fractions where the numerator is less than the denominator, which means that the value is less than 1. So these are things like 2/3, 3/4, 1/2, something like that. The numerator has to be less than the denominator. And since it's less than the denominator, that means that our value of whatever that fraction would be would have to be less than 1. So for example, these are things like 1/5, 2/7, 9/10. An improper fraction are fractions where the numerator is greater than the denominator, meaning that the value is going to be greater to or equal to 1. So an improper fraction includes fractions that are equal to 1. So if our fraction is equal to 1, that just means that our numerator and our denominator are the same value, because if we have 10 divided by 10, for example, that's going to equal 1, and that would be considered an improper fraction. So other examples would be 3/2, 11/7, 5/4, anything along those lines. As long as the numerator is greater than the denominator, that is an improper fraction, or if they're equal. So on to our first objective. So our first objective is identifying prime numbers. So beginning, we have a product is the answer to a multiplication problem, where the numbers being multiplied are factors of the product. So whenever we multiply two numbers together, you will result in a product. So for example, if we want to multiply 3 and 4, 3 times 4 is equal to 12. 3 and 4 would be considered our factors, while 12 is considered the product. A natural number greater than 1 is prime if it only has itself and 1 as factors. So it would be prime if that means that the factors would only be 1 and that number. So for example, 13 is a prime number. Its only factors are 1 and 13. Since no other numbers multiplied together to get 13, natural numbers that is. No, I'm not talking about decimals or anything like that. Then a natural number greater than 1 is composite if it has multiple factors other than itself and 1. So numbers are composite if they're not prime. And this just means that any number that can be multiplied or divided by multiple numbers will end up being composite. So these are going to be numbers like 12, because we see 12 has the factors of 3 and 4. It also has the factors of 2 and 6. So we see it has multiple factors other than just 1 and 12, and that makes it composite. Now, the number 1 is not prime or composite. Since 1 times 1 is technically just itself times itself, we see that it doesn't really count as prime and it doesn't really count as composite. So we just don't count it as either. But what we can do is we can identify the prime and composite numbers between 1 and 15. So let's begin. We have 1, which we know is neither prime or composite. And we're going to identify red numbers as prime and blue numbers as composite. And we're just going to write the numbers between 1 and 15, identifying if they're prime or composite. So if we consider the number 2, the only numbers that multiply together to get 2 are going to be 1 and 2. So 2 is a prime number. Then with 3, we see the same thing. The only factors of 3 are going to be 1 and 3. But now we want to consider 4. The factors of 4 are 1 and 4, but it's also 2. 2 times 2. So 4 is a composite number. Then we have 5. 1 times 5 are the only factors of 5. Then moving on to 6. 1 and 6 are factors of 6, but so are 2 and 3. Then 7. The only numbers multiplied to equal 7 are going to be 1 and 7. So 7 is prime. Then we have 8. 1 and 8 are factors of 8, but so are 2 and 4. So 8 is also composite. Then we have number 9. 1 and 9 are factors of 9, but so is 3 and 3. So 3 times 3 is 9. So 9 is also composite. Then we have 10. 1 and 10 are factors of 10, and so are 2 and 5. So 10 is composite. For number 11, the only factors are 1 and 11, so 11 is a prime number. Then moving on to 12, which we identified earlier as having the factors of 1, 2, 3, 4, 6, and 12. 12 is a composite number. Then for number 13, 1 and 3 are the only factors of 13, so 13 is a prime number. 14 has the factors of 1 and 14, and also 2 and 7. So 14 is a composite number. And lastly, we have 15. So 1 and 15 are factors of 15, and so are 3 and 5. So 15 is a composite number. All right, so that is kind of how we can identify prime and composite numbers between 1 and 15. Smaller numbers are always easier to kind of figure out since we often know common multipliers of relatively smaller numbers. When you start getting into larger numbers, you just want to begin by seeing if you can divide by lower prime numbers such as 2 or 3. So moving on to our objective 2, we want to write numbers in prime factored form. So we can factor a number by writing it as the product of 2 or more numbers. So what we have here is we have multiplication and factoring. So multiplication, we see typically things like 6 times 3 is equal to 18. 6 and 3 are going to be our factors, where 18 is our product. Then when we think about factoring, we're just reversing the order. It's essentially the same thing, we've just reversed the order instead. So with factoring, we see 18 as the product is equal to 6 times 3, which are factors. You may have noticed at this point that instead of writing a number times a number where we have an x, it's now being written as a dot b. This is just another way of saying multiplication. So these things are equal. So a cross b is equal to a dot b, and this is all multiplication. So they're the same things. Then we have a composite number written using factors that are all prime numbers is called prime factorization. So, for example, if we have the number 35, we want to find the factors of 35 that would end up giving us only prime numbers. So the factors of 35 are going to be 1 and 35, but we want values other than that. So the only other factors of 35 are going to be 5 and 7, both of which are prime numbers. So we can write 35 is equal to 5, that looks like a 6, 5 times 7. And both of these already happen to be prime numbers. So we consider these. They are prime numbers, so they're prime factors. So writing 35 as 5 times 7 is in its prime factorization. Another thing we can use is the factor tree to find the prime factorization of a number. So this is really useful if you have maybe larger numbers that are going to end up with multiple prime factorizations. Because what we're doing here is we want to take a larger number and we just want to express it in a way where we have multiplication of only prime numbers. So in this case, if we consider the number 36, we're going to draw a tree going down. So we have 36 and we draw two little lines to signify some number times another number. So 2 factors of our original number, which is 36. What the key here, something that you want to do, is you want to divide by the least prime factor of 36, which is 2. Since we can divide 36 by 2, we just want to use 2 times some number. So in this case, we're going to have 2 times 18, and 2 is our least prime factor. Then we just want to continue until we have only prime numbers. So the prime factorization of 18 is going to be 2 times 9. But now, since we have 9, we're going to have another factorization of more prime numbers. So once we factor 9, we see 9 is divisible by 3 times 3. So all of our prime numbers, which are now in red, we see are all prime. So we have 36, and we can rewrite this again. And I'm going to write this in green off to the side here. What we see here is that we get 36, and now we can say that 36 is equal to 2 times 2 times 3 times 3. Another note from our book here says that no matter which prime factor we start with when factoring, we will always obtain the same prime factorization. Verify that if we start with 3 instead of 2 in example that's in your book, you will obtain 24 is equal to 3 times 2 times 2 times 2. So the order of factors is different, but the same prime factors we will get in result. So in the case of 36, if we had begun with 3, we would still get the same answer. And that's because no matter which way you multiply numbers together, you'll always get the same answers despite the order. All right, so on to objective 3. We want to write fractions in lowest terms. These following properties are useful in writing a fraction in its lowest terms. So what lowest terms essentially means is that a fraction is in its lowest terms when the numerator and the denominator have no factors in common other than 1. This just means that you can't simplify your fraction any further. So going through these properties, we have properties of 1. So we have 2 items here. We have any non-zero number divided by itself is equal to 1. So an example, this would be 3 divided by 3 is equal to 1. So anything divided by itself is just going to be equal to 1. Then we have that any number multiplied by 1 is going to remain the same. So another example here would be 2/5 times 1 is still going to be equal to 2/5. So what this is telling us, in essence, is that if you take any number and you multiply it by any equivalent of 1, it's still the same. So we want to keep this idea in our mind for another future objective. So if we want to write a fraction in lowest terms, step 1, we want to write the numerator and denominator in factored form. Step 2, we want to replace each pair of factors common to the numerator and denominator with 1. And then step 3, we want to multiply the remaining factors in the numerator and the denominator. And this procedure is sometimes called simplifying the fraction. So we're going to do an example here. And our example here is 15 divided by 60. So what we're going to do is we want to write this fraction in its lowest terms. So step 1, we want to write the numerator and denominator in our factored form. So let's write it in our prime factorization form, or the best we can. So what we see here is we have 15 divided by 60. So if we want to write this in prime factorization form, we would write 15 as 3, that's a bad 3 times 5. And then we have 60 in our denominator. Now, at this point, you can either take a moment, pause the video, write out 60 with your factor tree to figure out what your prime factorization of 60 is going to be, which is going to be 3 times 2 times 2 times 5. So what we end up seeing here is that we have a 3 in our numerator and our denominator, and a 5 in our numerator and our denominator. So we can factor these values out. So this can become 3 divided by 3 times 5 divided by 5. And now what we have left over is a 1 divided by 2 times 2. Now we have to include this 1 because we know that 3 times 5 times 1 is the same as saying 3 times 5. but we have these extra factors left over in our denominator, which is 2 times 2. Using our properties of 1, what we see is that 3 divided by 3, 5 divided by 5 both become 1. So we're going to have 1 times 1 times 1 divided by 2 times 2 is going to be 4. Then once again, using our properties of 1, we see that 1 times 1 times 1/4 is still going to be 1/4. So simplifying our 15 over 60, we see it becomes 1/4. Now, we see that this here and this here both, ooh, this is a property of 1. Ooh. So we see that those became 1 by their property of 1. Another way that you could figure out how to do this is that we see 15 is going to be our greatest common factor. 60 is divisible by 15. So another way that we could have written this out is we could have also said 15 divided by 15 times 4. Because 60 is divisible by 15 and 4. And then this would end up giving us 15 divided by 15 times 1 divided by 4. And we get 1 divided by 4 since we know 15 times 1 is the same thing as 15, and we have to have a numerator with our 4, which was in the denominator. So it becomes 1/4. Then we know 15 over 15 becomes 1 by the property of 1. So we get 1 times 1/4, which will be equal to 1/4. Let's draw another little red arrow here. Property of 1. So there are 2 different ways you could do it. If it's not incredibly obvious, maybe what the greatest common factor would be in that moment, you can always break it down by the prime factorization and use that instead. So we can say here, just as a note, 15 is our greatest common factor. All right, on to our next objective. We have objective 4, which is going to be convert between improper fractions and mixed numbers. A mixed number is a single number that represents the sum of a natural number and a proper function. So if we had 5 and 3/4, that's the same thing as saying 5 plus 3/4. So for an example, we can write 6 4/7 as an improper fraction. So by saying we want to rewrite this as an improper fraction just means that we don't want it in a mixed number anymore. We just want a numerator and a denominator, and that's it. So if we want to factor this problem and we want to turn it into an improper fraction, we're going to have to figure out how to turn our number into a fraction. So if we have 6 4/7, we need to find a way to transfer 6 into some term of 7. And since it is a mixed number, what we can do is we can end up saying 6 times 7 is going to be equal to 42. And we would obviously need to have 6 in terms of 7 so that we can add up our fractions here. So we can say 6 times 7 is 42. Then 42 plus 4 is equal to 46. So we have 46, and this is going to be our numerator. Since we have our numerator now, we keep our denominator. and we get 46 divided by 7. So 6 4/7 is the same thing as saying 46 divided by 7. So what we saw happen here is that if we take, and let's do this in orange. So if we take our 6 4/7, what kind of happens here is that we can just multiply. I'll put a dot for multiplication. Or instead of an arrow, you could just write dot, however way you like. But what we're doing here is that we are multiplying 6 and 7 together. So like step 1. And then step 2, we're adding we're adding that product and 4. And then that becomes our improper fraction. So if we want to check our answer, we can always go in the opposite direction. We can always figure out if 46 divided by 7 is the same as saying 6 4/7. So we can say, to check, we can divide 46 by 7. So what ends up happening here is that we're going to have 7 divided by 46. Sorry, 46 divided by 7. I said that backwards, I apologize. So we have 46 divided by 7, and we have it in our division form. So we know that 7 can go into 46 6 times, which gives us minus 42, and we have a remainder of 4. So we can kind of label everything here. 7 is our denominator. 4 is our remainder. And 6 is our quotient. And lastly, 46 was our numerator. So now that we have divided out our numbers here, we write our final answer as the quotient, so 6, and our remainder divided by the denominator, which is 4 divided by 7. So let's label these just so it's a little more clear. What we did first here was we turned a mixed number, I'm going to write NUM for number. We turned a mixed number into an improper fraction. And then what we did here, let's use a different color. What we did here was we turned an improper fraction into a mixed number. All right, so we went both ways in essence in this one example. All right. So on our next objective, objective 5, we want to think about multiplying, and I wrote a D and not a G when I wrote this out. Oops, multiplying, there we go. We have multiplying and dividing fractions. So beginning with multiplying fractions, to multiply two fractions, we want to multiply the numerators to obtain the numerator of the product. Multiply the denominators to obtain the denominator of the product, and the product should be written in the lowest terms. So if we want to consider our value here, For our example, we have 3/4 times 5/9. So we want to multiply them together. This is going to give us 3 times 5 divided by 4 times 9. So we're going to multiply these values, and what this ends up giving us is 15, written poorly, 15, there we go, 15 divided by 36. But we want our product written in its lowest terms. So we see that the least prime number in both of these cases is going to be 3. So we can say 3 times 5, which was our original. Then we have 36 divides into 3 times 12. Then we want to use our property of 1 to write this as 3 divided by 3 times 5 over 12. Then using our property of 1, this just becomes 1 times 5 over 12, which is 5 over 12. So this was a problem in the case where we did multiply our fractions and then we had to simplify into our lowest terms. We couldn't just leave it as 15 divided by 36 since it's not simplified. All right, so now we have two fractions are reciprocals of each other if their product is 1, like in the table below. So our table here is just examples of reciprocals. So we have our number and then we have our reciprocal. So if our number is 3/4, where 3 is the numerator and 4 is the denominator, the reciprocal would be 4 divided by 3, where 4 is the numerator and 3 is the denominator. And we see that this is mostly because if we do take 3/4 times 4/3, we're going to end up with 3 times 4 divided by 3 times 4. Oops, sorry, 4 times 3, which is going to be 12 divided by 12, which is just 1. So if you can multiply them together and it equals 1, it's the reciprocal. So same goes for all the numbers below. So we have 11 divided by 7, the reciprocal is 7 divided by 11. The number 1/5, the reciprocal is 5, or 5 divided by 1, which is the same thing. And then we have 9, or 9 divided by 1, the reciprocal is going to be 1 divided by 9. If it's easiest to think about, the reciprocal is just your original fraction, but the numerator and the denominator are just flipped. So since division is the inverse or the opposite of multiplication, we can use reciprocals to divide fractions. So to divide two fractions, we want to multiply the first fraction by the reciprocal of the second. The result, or the quotient, should be written in the lowest terms. So looking at our image here also, when we divide fractions, we see we're looking at this image here. It's originally a circle. It's been separated into 8 parts. And what we see here is that we're really only considering 1/2 of the circle. So we want to take 1/2 divided by 4. And we're saying that this is going to be equivalent to saying 1/2 times the reciprocal of 4, which is 1/4. So we can make a lot of problems really easier. So instead of dividing by numbers or dividing by fractions, we can just multiply their reciprocal since multiplying is generally easier. So we have 1/2 times 1/4, which is equal to 1/8 of the circle, since we multiplied 1 and 1 and 2 and 4. So for our example here, we have 20 divided by 5/4. So instead of dividing, we want to multiply by the reciprocal. So this is going to give us 20 times the reciprocal of 5/4, which is 4/5. So we just flipped our numerator and our denominator. And now we can multiply these values. So this is going to give us technically 20 divided by 1 times 4 divided by 5, which will give us 20 times 4 divided by 1 times 5. which is going to be 80 divided by 5. And we know that 5 can factor into 80, or 80 is a factor of 5. We say 16 times 5 divided by 5, which is like saying 16 times 5 over 5, and using the property of 1, we get this as 16 times 1, which is just 16. All right, so our last objective that we'll be going over today is going to be adding and subtracting fractions. So the result of adding two numbers is the sum of the numbers. And I apologize, I should be in red. This is the sum, since this is one of our key words here. So when you add two numbers together, the result is the sum. So when we add fractions to find the sum of two fractions with the same denominator, we want to add their numerators and keep the same denominator. So this is the key if they have the same denominator. We can also consider our image here with adding fractions. We see we have 1/8 of the circle plus 3/8 of the circle. We see in this case here they do have the same denominator. So we're just going to add our numerators together, and that's going to give us 4/8, which we know we can simplify into 1/2. So for our example, we have 1/5 plus 2/5. Since they have the same denominator, this is like saying 1 plus 2 divided by 5, which will give us 3 divided by 5. Pretty simple. Now, if the fractions don't have the same denominator, we must rewrite one or more with a common denominator. So it could mean that we would need to rewrite both. So for example, if we have 3/4 and we want a fraction with the denominator of 12, we have to find the number that will multiply by 4 to get 12. So since 4 times 3 is equal to 12 by the property of 1, we can multiply the numerator and the denominator by 3. So using our property of 1, this idea that we mentioned before about how we really wanted to remember this one idea, we can multiply any number by 1 or anything equivalent to 1. And 3 divided by 3 is equivalent to 1. So what we get here is that 3 divided by 4, we can say multiplies by 3 divided by 3. And that's the same thing as 1. And remember, this is property of 1. And now we can simplify because we wanted our denominator to be 12. And we get that this is now 3 times 3 divided by 4 times 3, which is going to give us 9 divided by 12. So this process of writing an equivalent fraction is just the reverse of writing a fraction in lowest terms. So instead of having a fraction and finding common factors that can divide out or cancel each other out to get the lowest term, instead, now we're taking the lowest term and we're multiplying more terms to get a larger number, most oftenly with a different denominator. So our next idea here is finding the least common denominator. So to add or subtract fractions with different denominators, we want to find the least common denominator as follows. Step 1, we want to write each denominator in prime factored form. And step 2, the least common denominator is the product of every different factor that appears in any of the factor denominators. If a factor is repeated, use the greatest number of repeats as factors of the least common denominator. And step 3, we want to write each fraction with the least common denominator as the denominator using the second property of 1. This all to say that, for example, if we have 3/4 plus 2/8, what we can do is we want to write the denominator in the prime factored forms. So in this case, we're end up going to get 3 divided by 2 times 2. Then we have plus 2 divided by 8, which in its prime factored form is 2 times 2 times 2. So we see here on our right-hand side, we have one extra 2 in our denominator. So this means that we're going to take 3 divided by 2 times 2, and we're going to multiply it by 1, or the equivalent of 1, which is going to make it 2 divided by 2. And our second number is going to stay the same. We're still going to have 2 divided by 2 times 2 times 2. And we're going to continue this a little farther down. So now we end up having this 3 times 2 divided by 2 times 2 times 2 plus 2 divided by 2 times 2 times 2, which we can simplify this now. So 3 times 2 is 6 divided by 8 plus 2 divided by 8. Then this will give us 6 plus 2 divided by 8, which is 8 divided by 8, which is just equal to 1. So all we did in this sense was we wrote each denominator in prime factored form. We found the one value that was different, and we multiplied that value by our other term that didn't include it. Now, in some cases, you will have to multiply both numbers by different numbers if there isn't a least common denominator. But moving on. The result of subtracting one number from another number is the difference of the numbers. So instead of the sum, now we have the difference. So in subtracting fractions, to find the difference of two fractions with the same denominator, we just want to subtract their numerators and keep the same denominator. If the fractions have different denominators, we want to write them with a common denominator first, just like we did in our last problem, and just like we do when we add fractions. So looking at our image here, we have subtracting fractions. We have 8 pieces of a circle, and we have 3/8 minus 1/8. So we're subtracting a 1/8. And this is just going to give us 2/8, which simplifies to 1/4. For our first example, we're going to have 5/7 minus 2/7. So we have two values with the same denominator. This is just going to give us 5 minus 2 divided by 7. 5 minus 2 is just going to be 3, so we have 3 divided by 7, and that'll be our answer. Then we have one more example that's important to show. We have 15 divided by 16 minus 4 divided by 6. So if we just consider our denominators, 16 and 9, if we want to write them out in our prime factorizations, what we see is that we're going to get 15 divided by, you can take a moment to find the prime factorization of 16 if you'd like, but it's going to be 2 times 2 times 2 times 2. Then the prime factorization of 9 is going to be 3 times 3. So what we see is that they don't have any factors in common. One has only 2's and one has only 3's. So what's going to happen is that we need to multiply 16 and 9 in both of these terms. So let's make this a note here. We say, since there are no common factors of 16 and 9, the least common denominator is 16 times 9, which you can take a moment to calculate this if you'd like, is going to be 144. So we have 15 divided by 16, and we want the denominator to be 144, which means that we need to multiply our denominator by 9. And we can multiply anything by 1 or an equivalent of 1. So with our first term, our 15 divided by 16, we need to multiply this by 9 divided by 9. Then with our second term, since we have 4 divided by 9, and we need to multiply 9 by 16 using our property of 1, we can say multiply by 16 divided by 16. And now we just want to multiply these values. So we get 15 times 9 over 144 minus 4 times 16 over 144, which if we simplify these will be 135 divided by 144 minus 64 divided by 144, which when we subtract these values, feel free to use a calculator at any point, this is going to give us 71 divided by 144. And our 71 divided by 144 is in its most simplest form. So that would be our final answer when writing out 15 divided by 16 minus 4 divided by 9. All right. Then moving on here, objective 7, which is going to be solve applied problems that involve fractions, and objective 8 is going to be interpret data in a circle graph, are going to be continued in our class tomorrow, which is going to be Tuesday, January 26th. So we will do problems from these sections to complete our objectives, along with other problems that are going to be similar to the ones that we saw here in class today. Also, just as a reminder, at the end of our class, we do have office hours. So if you would like to stick around for office hours at any point, you can feel free to do that. And if not, I am looking forward to seeing you all tomorrow and meeting you all officially. So have a great day, everyone, and I'll see you tomorrow.